Hi, welcome to es346 Basic Thermodynamics. These are examples, and this example is an R134A Carnot heat pump. I'm Roy Peterson. Here's the example problem we're going to go ahead and solve. We're told we have an R134A Carnot heat pump, and it operates with an absolute temperature ratio of 1.25. The power requirement is 7 kilowatts, and the mass flow rate is given at 0.25 kilograms per second. We're also told that the heat rejection step involves complete liquefaction, and we're asked to find what is the pressure ratio. Okay, so in the diagram over here on the right, we see is a typical heat pump where the heat rejection step up here goes up to a high temperature, and I'll call that TH, and heat absorption comes down over here at a temperature TL, and over here is my work requirement. But I'm given what the temperature ratio is, but I'm asked to find the pressure ratio, and that may not be obvious. So let's go ahead and draw this process on, for example, a TV diagram relative to the saturation curve. And we're told that the heat rejection step involves complete liquefaction. And so if you remember what the Carnot heat cycle looks like, we've got sort of a rectangle down in this region. And this step right over here is the heat rejection step, QH. This step down here is the heat absorption step, QL. And then we have a work requirement that goes in, which is typically that step right there. So we know that since it involves complete liquefaction, we're going from a quality of x equals 1 over here to a quality of x equals 0. And if you see how this curve kind of gets smaller near the top and larger near the bottom, that actually correlates to a different amount of enthalpy. So it sort of fixes where that upper line is. And so we've got a temperature over here, which is TH. We have a temperature down here, and that is TL. We know that ratio is 1.25. But the other thing we know is that going across to saturation, both of those points correspond to a saturation pressure. So that would be Psat at a high temperature, and this down here will be Psat at a low temperature. So if I know the ratios of the temperatures, I would know the ratios of the pressures. Well, it's not quite that simple, but if I determine what each of these temperatures are, I can then go ahead and find out what the pressures are. And that's the way we're going to go ahead and solve that problem. All right, so let's go ahead and look what we're given and what we can kind of figure out. So we're over here, and we're told that the absolute temperature ratio is 1.25. And if you recall, the coefficient of performance for a heat pump that is reversible, that's a Carnot heat pump, is this ratio right over here, is 1 over 1 minus TL over TH, where those temperatures are absolute. And the problem gives me that ratio at 1.25, so I can go ahead and find this as 1 minus, and this is TL over TH. I'm given TH over TL, so it's 1 over 1.25. So that's going to go ahead and give me a coefficient of performance of 5. Now recall, coefficient of performance, that's sort of how well we're leveraging this. So it tells me for every 1 kilowatt of energy I bring in over here, I'm actually going to end up with 5 going in up there. All right. Now recall what the coefficient of performance for a heat pump is. It's the desired over the required. And so what we desire from heat pump is getting my QH, and what's required is the net work over there. And we're told what the net work is, and the net work is 7, so I can write this as QH over 7, and I know that that is equal to 5 because I just solved for the coefficient of performance. So therefore, I can quickly go ahead and find out what QH is, and QH is going to be equal 7 times 5, or 35 kilowatts. And that's kind of what we were just mentioning. We're leveraging every 7 kilowatts we're putting in, we're multiplying it by 5, we're getting about 35 kilowatts of heat. And that's why heat pumps can be pretty efficient devices that we have. All right, well, we haven't really determined anything in terms of temperatures here, but now we know what this value of QH is. And recall, this is this step right there, and we know that that is 35 kilowatts. And so if we do an energy balance over just across that step right there, QH is going to end up being equal to the mass flow rate, this is in terms of a rate, times this is going to be HFG. So that right up there is my change in enthalpy as I go from a quality of 1 to a quality of 0. And I know that that right there is equal to 35 kilowatts. So I can then go ahead and solve for HFG. I'm given what the mass flow rate is. So HFG is going to end up being equal to 35 kilowatts. Divide that by my mass flow rate of 0.25 kilograms per second. That's given in the problem. And so that goes ahead and gives me a value of 140. And my units there are going to be kilojoules per kilogram, because I have kilowatts, which is a kilojoule per second. Mass flow rate, kilograms per second. The per seconds cancel, end up with kilojoules per kilogram. And that's 140. So that's the enthalpy of this upper step I have. And now with this value, I can actually determine what this temperature is, this value of pH. And how do I do that? Well, what I want to do is I'm going to go to the saturation tables. And so let's go ahead. In fact, we can actually directly find out what Psat is as well. So I'm going to go over and go to the saturation tables. And we want to go ahead and do that for a refrigerant R134A. So I need to kind of scroll down a bit here. This is water. We'll go past the water tables in the superheated water. And we get down to, okay, here's refrigerant R134A. All right, so what we can do, if we look at this value HFG, and we realize as the temperature gets larger, looking down, the numbers get smaller. And if I go ahead and scroll down a little bit further, what I'm looking for here is a value of 140. And actually looks like I got to go to the next table here. So here's HFG. All right, again, I'm looking for a value of 140. And I see that it's going to fall between these two lines right over here. So it's somewhere between 60 and 56 degrees. All right, so I want to go ahead and interpolate to find out exactly what that temperature is. So remember, I'm between 56 and 60. I'm interpolating 144.41, 139.09. Okay, so I'm going to go ahead and give myself a new sheet over here to go ahead and I'm just going to do an interpolation here. So for H140 was my value of HFG, and I'm interpolating between 139.09 and 144.41. So 139.09. All right, so that ratio there is 0.171. And so that, and now I'm interpolating between the temperatures of it was 60 and 56. So T minus 60, and this would be 56 minus 60. All right, now note that this temperature 60 correlates to the number of 139.09 and 56 corresponds to 144.41. So those two things are symmetric. And from there I can go ahead and solve for the temperature, and that is 59.3 degrees Celsius, and that is the high temperature. And if I convert that into Kelvin, that is 332.4 Kelvin. Right. So that's my temperature. That's TH right there. And if I want to know what the pressure is, I got to get the pressure ratio. I want to find the corresponding pressure at that temperature as well. And so I'm going to again use this value of 140. So let's go back to our tables. And now I'm going to go ahead and go to the pressure table. So let's go ahead and go back to oops, no, actually the pressure table is the next one down. So it's okay. So here we go, and we're looking for 140 again. So here's my value of HFG, and I'm looking for 140. So I'm down here between this 141.96 and 135.14. And that's going to be a pressure of 1600 and 1800. So let's go ahead and interpolate that pressure value. So again, over on my sheet over here, we're now going to be looking at what our pressures are. So I have 140 minus 135.14, and that's going to be in 141.96 and 135.14. So those are off that pressure table. 0.7126 is that ratio. And so now this is going to be my pressure, and that was between 1800 and 1600. So 1600 is 1800. And now I can go ahead and solve for that pressure, and that pressure is equal to 1650. Oops, sorry. Let me erase that there. Where's my eraser? Okay. That was 1650 347, and that is kPa, and that is the high pressure, so that is pH. Alright, so now I know what my high pressure is, and I know my high temperature. So what we want to do now is get our low temperature. So if we come over here, we just found out what T low was, we just found out what T high is. We want to find T low. We know those ratios are 1.25. So I can actually solve for T low. That's going to be T high over 1.25 using that ratio right there. So that's going to be T high. We interpolated 332.4 over 1.25. Gives me my low temperature of 265.9 Kelvin. That right there is going to be equal to minus 7.2 degrees Celsius. All right, so there's what my T low is, and now I'm going to find out what the corresponding pressure is at that temperature right there. So what do I need to do? Well, we need to come back to our tables here, and we're going to interpolate given what our temperature is. And I could actually use either table. I'm going to go ahead and use the temperature table here. All right, so what we were told is we're at minus 7.2, so we're going to do minus 7. Oops, nope, let me use the pressure table. That's what I have values for. You can use either one. I happen to do my example here with temperature. Oops. All right, so we're looking at minus 7. Okay, sorry. All right, there we go. Okay, so we're looking at minus 7 degrees, and it's between 10.09 and 5.38. So the pressure is going to be between 240 and 280, or sorry, between 200 and 240. So let's go ahead and do that interpolation. All right. So this is our final interpolation that we have. We had minus 7.2, and this was between minus 5.38 and minus 10.09 that was minus 5.38. So I'm trying to find that corresponding pressure. That ratio is 0.386, and that was between the pressures of 240 and 200. So oops, I'm writing myself a little too fast here. So let's come back. And so that was between 200 and 240. And now I can go ahead and solve for that pressure. And that pressure is 224.5. And that right there is the low pressure. So there's my high pressure, and there's my low pressure. So we can go ahead and solve our pressure ratio, which is pH over PL. Put in our numbers there. 1657 over 224.5 gives me a pressure ratio of 7.38. So that goes ahead and solves this problem. So a lot of steps in terms of interpolation, but once you kind of get that down, it kind of becomes second nature.